Am I audible, students?
Yes, ma'am.
Yes. Okay. Good afternoon, all of you. Today, the CS department has arranged the guest lecture for computer graphics subject. All the second year students, that is regular students as well as direct second year students, are invited for this particular lecture. Today we have guest faculty, Professor Rajkumar Panchal sir. So he is working as assistant professor in Vidya Pratishthan College of Engineering, Baramati, which is under Pune University. He has, so let me introduce him first. So he has completed his BEIT from MS Bidway Engineering College, Latur, with distinction. Then he has completed Master of Technology from Dr. Babasaheb Ambedkar Technological University with a CGPA 7.41. Currently, he is pursuing his PhD from SGGS College of Engineering, Nanded. He has done his coursework till now. So he is having a total teaching experience in various fields, like, or various subjects. He is working in the VPCOE college since 2012. So total he is having 8 to 9 years of teaching experience. In that experience, he has taught many subjects like object-oriented programming, discrete mathematical structures, computer graphics, software testing and quality assurance, then numerical methods and computer programming, principles of programming language, information and cyber security in UG level. So he has great experience in computer graphics also. So I request all the students to take benefit of his teaching, and he will be clearing your doubts for this chapter number 6, plane curves and space curves, which is under computer graphics. So you are requested to participate with full enthusiasm and take 100% benefit out of his knowledge. So I request 100% attendance plus participation from student side. So I request Sir Panchal sir to please start the session.
Thank you, madam. So instead of this expert lecture, I would say this is a discussion. Whenever I discuss anything, whenever I am in the lecture, at that time, always I would like to have a discussion instead of one-way communication. Because if we have a discussion, then that will be effective way to understand and to get involved all the students and me also. Okay, so in computer graphics, so let's start this session instead of discussing some other things. Let's start this session. So in computer graphics, till now, probably you may have learned from the simplest things to the complex thing. Like possibly you have started the computer graphics with the introduction where you have seen how a point is plotted on the screen by using the Cartesian coordinate system, by using X and Y coordinate. Okay, then you may have moved towards how we can, by the help of these pixel, how we can draw the line, how we can draw the circle for drawing line and for drawing circle. Probably you may have seen several algorithms like DDA or Brasenham, or for circle drawing, we are having one extra algorithm that is midpoint. I don't know it is there for your syllabus or not, but as far as my knowledge. For circle drawing, we are having three algorithm: DDA, Brasenham, and midpoint. And for DDA and for line drawing, we are having DDA and Brasenham. Okay, so these things you may have studied. After that, you may have a polygon. Uh, do you have this unit related to polygon?
Regarding polygon filling, the algorithms are there,
Okay.
and 2D and 3D transformations are there for polygon.
Fine. Okay. So basically, when I used to teach this polygon, a student may ask like, why do we have a special unit on this polygon? Because whenever we see a computer graphics or whenever we create any object by using any animation tool or any digital tool, at that time, all the objects are created with the help of polygon. Okay, so if we are creating a monkey face, if we are creating any cube or anything, so all these surfaces are typically created by interconnecting polygon to each other. So that's why in your study you may have a polygon, special unit related to polygon. Okay, so probably you may have seen that. And then after that, in computer graphics transformation in day-to-day life, whenever we are observing anything on digital display devices, at that time we may have performed this transformation, like we may have rotated, we may have scaled, we may have slanted, we may have deformed some of the things, we may have shifted some of the things. So like this, these are some of the operations that we may have performed which are related to transformation. Okay. Then after that, you may have studied visibility, which are the visible surface, which are the invisible surface, then color model, and there are some illumination things. So these are some of the things that are in general included in computer graphics. Basically, this computer graphics, it is introduction to image processing. Probably in final year you may do a project, you may accomplish the project in image processing if someone is interested, or in day-to-day life we are performing this image processing. We usually perform clipping, we may do a Photoshop like of things. Okay, so computer graphics start with the simplest thing like a point or polygon, which we can, point or a pixel that we can control. And slowly from this point, how we can construct a line, circle, how we can construct a field polygon, how we can apply various model, all these things we have observed. Okay, And if you want to draw a curved surface, at that time it is possible to draw a curved surface by using a polygon, but that is somewhat difficult thing. So for this purpose, the last unit that we are going to observe that is related to curve. Plane curve and space curve. These are the two concepts. Plane curve means whatever things we are observing on two dimensions. That is nothing but that is the plane curve which we can draw in two dimensions. Space curve specifically if we have a three-dimensional things, three-dimensional space. In this case, we want a 3D object or a 3D curve. So that is nothing but that is the curve. Okay. So let's see the concept of curve, how we can draw a curve, and how in real life we are using these things for creating various objects. Okay. So when we talk about the curve, at that time, there are various ways by which we can draw a curve, which are called as curve generation method. Okay. So basically, in computer graphics, we uh, frequently use a curved object, different object for displaying different things on a virtual screen or on a digital screen. Okay. Basically, these objects are not always flat. Okay. There are some objects which we can say that these are curved in shape. Okay. So if we want to get such curved surface, for drawing such curved surface, we must know how we can generate different type and different shapes of the curve. So for this purpose, basically, if we want to define the definition of a curve, then curve is something which is a collection of, we can say, a point which lies in the circular path or in the we can say slightly curved path. Okay. So for this purpose we may observe such things. Okay. So curve is nothing but it is an infinitely large set of points, and each point has two neighbors whenever we are discussing about the curve, except the start point and end point. Each point will have the we can say two neighboring, one on the right side and one on the left side. Okay. So let's see how we can generate a curve by using the existing knowledge. So whenever we are moving, whenever we observe any new things, at that time, always I start from the known things and slightly we move towards the unknown things. Okay. So probably you may have learned circle generation algorithm, and there is one method which is called as DDA curve generation method. So to generate a curve, as per our existing knowledge, we are having two methods or two techniques by which we can draw the curve. One method is nothing but we are having a DDA curve generation method where we specify some of the things. We will see, in short, we will see what is this DDA curve generation method. And if we talk about the circle generation algorithm, then probably you may have seen that there is a center, and around the center we are drawing a circular path, circle. Okay. So basically, whenever we are drawing a circle by using any algorithm, at that time, all the algorithm draw the circle in a first quadrant, right? Is it correct? DDA algorithm ni DDA algorithm जो आहे, everyone, I think everyone understand Marathi. So in DDA algorithm, specifically this algorithm is developed to calculate the points in the first quadrant only. And how do we get the remaining part of the circle? Does anyone know? Or probably you may have implemented these algorithms. माहिती आहे कोणाला? How we draw this whole circle? Algorithm, by the help of algorithm, what we are doing, we are drawing just a first quadrant part, and remaining part of the circle we are drawing by using the reflection, right? So what we do, we use reflection, and by reflecting the things we are drawing the whole circle. That is what we are doing basically whenever we are drawing a circle. Now, by the help of this circle generation algorithm, we can draw the curve. How we can draw the curves here? So instead of reflecting the points in remaining quadrants, what we can do, let's say if we want to draw a curve which is of this shape. Okay, for drawing this shape of curve, what we can do, we can execute the circle generation algorithm from this point till this point. And with the help of this, by using a circle generation algorithm, we can draw a curve. So this is the one way by which we can draw a curve. Okay, so let me erase these things. Okay, then we are having next way, which is nothing but by using DDA curve generation method, DDA curve generation algorithm. So let's see how we can draw the curve by using DDA curve generation algorithm, DDA curve generation technique. In DDA curve generation technique, what we are doing, firstly, we need to provide the end point of the curve. That is, from which point we want to draw a curve and at what point we want to stop drawing this curve. Say, for example, we want to draw a curve from point x1, y1 to x2, y2. Okay. Then in DDA curve generation method, what we have to do, we have to provide these coordinates from which point we want to start the curve generation and at which point we want to stop. Okay, so basically these points we can explain in correlation with the center. Okay, so in DDA curve generation method, what we have to provide, we have to provide the starting point of the curve, then end point of the curve, and along with this, we need to provide what is the center of this curve generation of this curve and what is the radius. Okay, and with the help of this information, DDA curve generation method draw the curve. Okay, so here yc is nothing but it is the y coordinate of the center, and xc is nothing but it is the x coordinate of the center, and r is nothing but it is the radius of this curve which we want to draw. Okay, so by the help of the information that we have, that is center of the curve and radius, what we do, we specify the starting point, that is what x1, y1, and from this point, DDA curve generation method start drawing the curve. Okay. Say with the help of this information, it will plot the first point which is on the curve. Say for example, it will plot this point which I am specifying by using a blue point. Okay. Then next, we need to draw a second point, third point, fourth point, fifth point. Like this, it will go on drawing the point. Now, how this curve generation method draw these points? Let's see this. Okay. After drawing the first point, that is from the center, it will move horizontally r direction away from the center, and it will plot the point x1, y1. Okay. Then to plot the second point, that is the neighboring point of this x1, y1, which is on the curved path. For this purpose, what it will do, this DDA curve generation method take the help of equation, and that equation is nothing but the equation is this one. Okay, so let's say the coordinate of this next x point, it is xy. This is the say coordinate of this point. Now how this xy coordinates are calculated, we are having a center of the circle. In this center, basically this DDA curve generation method, it will add this amount where this r is nothing but this is the radius of the circle, and theta is called a stepping angle. What this theta is called? Theta is called a stepping angle. What do you mean by stepping angle? Let me show that. So here we are having a curve, right? And here we are at the start position here at this point. Okay. And we want to plot this point. Now to plot this point, what we can do, we can take the angle, this angle, this small angle is called as stepping angle. This is called as stepping angle. Okay. With the help of which we can calculate the next pixel that we can turn on to draw the curve. Okay, so this is what the stepping angle, and this stepping angle increase as we move from the starting point, that is from x1 y1 point. As we move away, this stepping angle gets increased. Let's say initially this stepping angle may be 1 degree, after that it may be 2 degree, after that it may be 3 degree. So like this, by using by increasing this stepping angle, we can plot, we can display the pixel on the curved path, and the final result by executing this DDA curve generation method is what? It will draw, it will display whole curve by turning on the pixel along the curved path. Okay. So with the help of this DDA curve generation method, it will generate, it will display the curved path. Okay. So this is the way by which DDA curve generation method works. Okay. And second method we have seen by using a circle drawing algorithm, that is DDA or Bresenham, or we are having midpoint circle generation algorithm. By the help of these algorithm, we can prefer to draw a specific part. Okay, and by drawing this specific part, we can generate a curve. These are the two existing method, or these are the two known method with which we are somewhat familiar, with the help of which we can draw the curve. Okay, so these are some of the existing ways by which we can draw a curve. Okay, but if you observe this curve generation method, there are some drawbacks, or we can say there are some lacunas, disadvantages of these methods. Okay, so whenever we want to draw a curve, at that time, for drawing curve, what we want, we just want to provide the starting point of the curve, and we just want to provide the ending point of the curve. With the help of this information only, we want to draw a curve. But if we are using this DDA curve generation method or any circle drawing algorithm to draw a specific curve, for this purpose we have to provide lot of information, like we need to provide the center of this curve, we need to provide the radius of this curve, we need to specify the stepping angle of this curve. So lot of information we have to provide if we want to generate a curve by using this DDA curve generation method, or by using a circle any circle generation algorithm. Okay, so this is the first drawback of the existing method that we can use for drawing the curve. Okay, apart from this, there are some more drawbacks, like if we apply scaling operation. Scaling means increasing or decreasing the size of the curve. If we apply the scaling operation on this curve, then some of the basic properties get changed, like the shape of the basic curve, it may get deformed, or it may get changed. Okay, so this is the second drawback which we generally have, which we generally feel whenever if we use DDA curve generation method, or if we use any circle generation method for drawing a curve. Then the next drawback that we have is if we want to perform a clipping operation, if we are interested in extracting, in observing a specific part of this curve, then performing this clipping operation is somewhat difficult if we are using this DDA or any circle generation algorithm. Apart from this, we have observed that it is not simple to implement these methods like DDA curve generation, or we can say any circle generation algorithm for drawing the curve. Okay, so these are some of the drawbacks that we have in the existing curve generation method, probably that you may have studied in the first, second, or third unit. Okay, so to avoid this drawback, to remove this drawback, new method was developed, and that is called as curve approximation method. Okay, so in curve approximation method, what we are doing, we are specifically using the equation, parametric form of equation we are using, and by using this parametric form of equation, we can draw a curve. Okay, so we can draw a curve. Specifically, we are going to use the Lagrange interpolation curve, Lagrange interpolation method, with the help of which we are trying to draw the curve. For this purpose, we are using parametric equation for drawing the curve. Basically, if we observe the information about this interpolation method by using the curve approximation, then with the help of this interpolation method, what we are able to do, we are able to create a smooth curve that passes through the points with which we want to draw the curve. Okay, so let me explain these things. So what we have, let's say we want to draw a curve which is of this shape. If we want to draw a curve of this shape, then for this purpose, in this curve approximation method, what we are doing, we are using the group of points, and these group of points with the help of which we are trying to draw the curve, these group of points are called as control points. Let's see how with the help of these group of points we can draw the curve. Let's say we want to draw such curve. For drawing such curve, what we can do, we can take some of the points which are along this curved path. Okay, and what we can do, we can use the line drawing algorithm to connect these points, and with the help of this we can get the curve. Like let's say these are some of the control points, these are called as control points which controls the shape of the curve. Okay, we are trying to observe how curve approximation method generate the curve, smooth curve. Okay, for this purpose, let's consider that we want to draw such curve. Okay, to draw this curve in curve approximation method, firstly we are trying to calculate the control points. These are some of the sample points, these are the group of points using which we can approximate the shape of a curve. Okay, so once in this method, once we get the sample point, what we do, we simply connect these sample point by using the small line segment like this. We simply draw the line segment between these points. Okay, so these are the small line segments that we are drawing. Okay, and by using this line drawing method, and with the help of this we can say sample point, with the help of these control points we can draw the whole curve. Okay, now if we want a smooth curve, to draw a smooth curve, what we need, we need more sample points. Okay, if we have less sample point, then the shape of curve is not smoother. If we want a smooth curve, for drawing a smooth curve, what we need, we need a sample points, we need a control point which are closer to each other. More the control points, more the smoother curve that we get. Okay, now here the thing is, how we can draw, how we can calculate these sample point. That is the question that we have. Okay. So specifically, what we are doing here to calculate the step size, what we are doing, we are using the specific method. We are using the approximation method. We are using the interpolation technique. Now, what do you mean by interpolation? Interpolation means if we have two values, calculating the values in between the given values. That means, let's say we are having value 1 and 4. Calculating the values which lies between 1 and 4, this is called, in simple word, this is called interpolation. Okay. So to get this sample point, to calculate this intermediate point which lies along the path, we use this Kerr approximation method. We are using the interpolation technique. What we do? We use interpolation technique to draw this curve. Now, in this interpolation technique, what we are doing, we are using, or we want to generate a curve by using an approximation method. Then for this purpose, we can use the parametric form of polynomial function. Okay. Say for example, to get the x coordinate, we can use the parametric form of equation which may be in this form, fx of u. Okay. Which is a function of x. By using this parameter u, it is providing the x coordinate for drawing the curve. Then we are having a y coordinate. If you want to get this y coordinate, for this purpose, we may use one more polynomial function. Let's say that polynomial function is fy of u. Okay. So by the help of these polynomial function, so this is for 2 dimension. If we want to draw a 2D curve, then what we do? We will use a polynomial function for x and y only. If we want to draw the curve in 3 dimensions, for drawing the curve in 3 dimensions, what we can do? We can use the third function also, third polynomial function, which is in the parametric form, which is nothing but which is fz of u. Okay, so this is for 3D. So by using this polynomial function, by using this parametric form of polynomial function, we can draw the curve. Now the thing is, how do we calculate this fx of u? How do we calculate this fy of u? And how do we calculate this fz of u? Now suppose that we want to draw the curve, and to draw this curve, what we are doing? We are using the control point. Let's say there are n control points, and the coordinate of these n control points are x1, y1, z1, x2, y2, z2, like this up to xn, yn, zn. These are what? These are the control points that we are using, that we want to use for drawing this curve. Okay. So this parametric form of polynomial function we get by using these coordinates. How do we get this? See here. What we do here, the curve function can be constructed by making the addition, by doing the summation of these terms. Okay. For one control point, we are having one coordinate. Okay. And we are using a blending function. What is this blending function? We will see soon. Okay. So for calculating this fx of u, what we can do? We can take a summation. In mathematical term, this is denoted like this. So I varies from 1 to n. Okay. So here xi and bi of u, where what we can say, this bi of u, this is called blending function. Okay. This bi of u is called a blending function. Right. So this parametric form of equation is nothing but it is the summation of x coordinate of the point which we are using, which we want to use for drawing the curve, and along with this x coordinate we use blending function. What is the purpose of this blending function? By the help of this blending function we will get the curved, what we can say, curved field, curved surface, by using this blending function. Okay. Now let's say, for example, if we want a blending function for x1, then this value of this bi of u, it will be 1 for x1 only, and for x2, for x3, up to xn, for all other x coordinate, this blending function, that is what b1 of u will be, what it will be 0. Okay. So we are having this blending function, and this blending function will be 1 for specific coordinate. Let's say, for example, if we want, if we are using this blending function for x1 coordinate, then this blending function is such that this blending function will be 1 for x1 value 1, and this b1 of u, it will be 0 for other x coordinate. So this is the nature of the blending function, and by using this blending function and by using the x coordinate, which are the coordinate of the control points which we are which we want to use for drawing this curve. Okay. So this is the blending, this is the parametric form of equation for x. Similarly, parametric form of equation for y is this one. So in symbolic format, we may write like this: I varies from 1 to n, yi and bi of u. In this format, we can write this equation. Okay. So we use these two parametric form of equation if we want to draw two-dimension thing. If you want to draw two-dimension curve. If we want to draw three-dimension curve, in that case, what we can do? We can use the third coordinate, and this third coordinate is nothing but it is fz of u. Okay. So here what we do? We are making the summation of z coordinate along with its blending function. Okay. So this blending function will be such that this blending function value will be 1 for specific coordinate. म्हणजे blending function जो आहे, this blending function, it will be 1 for x1, and for other it will be 0. For x2, this b2 of u will be 1. Okay. And this b2 of u, this blending function, will be 0 for x1, x3, x4, up to xn. For all the other things, this blending function b2 of u will be 0. Okay. So like this, with the help of blending function, with the help of this parameter u, what we are doing? We are trying to draw the curve in curve approximation method. Okay. So this is how, by making the summation of all these terms, all the x coordinate along with its blending function, all the y coordinate along with its blending function, what we can do? We can draw the curved surface. Okay. So whenever we decide the control point for the curve, then what we can do by using the blending function, by calculating the blending function, we can draw the curve. Okay. So if I expand the equation which we have seen in the previous slide, then this equation will look like this. So x1 b1 of u, x2 b2 of u, plus x3 b3 of u. Like this, by making the summation of these equation, parametric form of equation, we can draw the curve. Okay, where if you observe, n is nothing but n specify the number of control point that we are using for drawing the curve. Xi is nothing but it is the x coordinate corresponding to ith control point. Y is nothing but it is the y coordinate corresponding to ith control point. If we want to draw a three-dimensional curve, then what we have to do? For z also we have to perform same thing, right? So z1 z1 b1 of u, z2 b2 of u. Like this, we have to add the z term along with its blending function, and with the help of this, we can get three-dimensional curve by using approximation method, curve approximation method. So specifically what we are doing here, we are using Lagrange's interpolation for calculating the intermediate point. Okay, so this is the first method with the help of which we can draw, we can generate the curved path. We can generate a curve. Some of the examples are like this. We can generate a curve like this. So here you are observing this is the control point. This is one control point. This is another control point. This is the third control point, fourth, fifth, sixth, seven, and eight. For drawing this curve, we have used 7 control points. And by using the equation, that is the parametric form of equation, what we can do, we can generate such curve. Okay, so this is the first method with the help of which we can generate the curve. Now here, if you observe specifically, this is not a smooth curve because here there is a sharp, we can say, there is some sharpness in the curve. Okay, so this is not a smooth curve. So if we want a smooth curve, then probably instead of one control point, here we may have used 3 control points. So with the help of which we may get such curved path, smooth curve. Okay. So this is the first method with the help of which what we can do, we can draw the curve by using curve approximation method. In this curve approximation method, we are using blending function. We are using parametric form of polynomial function with the help of which we can draw the curve. Okay, so this is the first method. Let's see some more methods which are related to curve. We are having next method which is called as B-spline line curve. Now, just now we have seen if we want to draw the smooth curve, to generate a smooth curve, we use interpolation technique. And to generate the smooth curve, we are putting one condition, and that condition is nothing but all the points, that is, curve must pass through the sample point. Okay, and with the help of this restriction, we are getting a smooth curve. Okay, so these are the two we can say guidelines which we are using whenever we want to draw a smooth curve. Okay, apart from this, what precaution we are taking, the sum of blending function must be 1. Now how this B-spline curve generation method works, let's see. In this B-spline curve generation, we are using 5 sample point. We are using 5 sample point for drawing the curve. Okay, these sample points are arranged in this format. So this is the first sample point. Here we are having first sample point. Here we are having second. Here we are having third sample point. Here we are having fourth sample point, and here we are having fifth sample point. Okay. Now What we will try? We will try to accomplish, we will try to fulfill these criteria. So to draw the curve which will pass through these sample points, what we are trying? We are trying to draw the curve which must pass through these sample points. Okay. Now for this purpose, what we can do? We may draw the curve which is like this. Okay. So what we are doing? We are connecting the first and second sample point, let's say by using such curve. Second and third sample point we are connecting, let's say by using this curve. Third and fourth sample point, let's say we are joining by using this curve. Fourth and fifth by using this curve. Okay. So here we are fulfilling the criteria. That is, for drawing a curve, what we are doing? We are satisfying the restriction, and that restriction is our curve is passing through all the sample points. But if you observe the nature of curve, this curve is not a smooth curve. Here you are observing sharpness of the curve, right? So what you are observing here? Sharpness. Here also you are observing some sharpness. Here you also you are observing sharp nature of curve. This is not a smooth curve. If we want to get a smooth curve, then we must remove the sharpness. We must remove the sharp corner. Why we are getting this sharp corner? We are getting this sharp corner because here, what we can say, here the nature, here we are joining the curve at the specific sample point. Now, that means if you want to draw a smooth curve, then we must relax the condition. Which condition we must relax? That condition is all curve must pass through the sample point. Must pass through the all sample point. This restriction we can relax by removing or by relaxing this condition. We can get a smooth curve in B-SP line curve. Okay. So instead of restricting the curve to pass through all the sample points, what we can do? We can restrict the curve to pass through only one sample point, and with the help of which we get the curve which is of this nature. Again, if we observe here, here we are not getting a smooth curve. Here we are not getting the smooth nature of the curve. Okay. So what we have did here? We have relaxed a condition. That what condition we have relaxed? We have relaxed a condition that this curve must pass through all the sample points. This condition we have somewhat relaxed. Now, if you observe, the curve is passing nearby this sample point. Now, this curve is passing nearby this sample point. Okay, it is not passing exactly through the sample point. And with the help of this relaxation, we are getting somewhat smoother curve. Okay, right? But here we are not getting a smooth effect at this point. Okay, so to get this smooth curve, what we can do? We can relax again. We can relax the condition again. So instead of restricting the curve to pass through the all sample point, what we can do? We can relax the condition so that we get a smooth curve like this. Now here, what we are doing? We are relaxing the condition. We are removing the condition that the curve must pass through the sample point. Instead of that, now we are restricting the curve such that this curve is passing nearby the sample point. Okay, so this is the way by which BSP line curve generation method works. Okay, in this BSP line curve generation method, specifically, we are using 5 control points and we are drawing a curve such that this curve is passing nearby to the sample point, and with the help of this we are getting a smoother curve. Basically, the meaning of BSP line is nothing but we are assuming there is a strip line, there is a strip of we can say any object, there is a strip of plastic or there is a strip of iron. Okay, and we are basically folding the strip of we can say any object nearby the sample point. SP line means it's a strip of a line, strip of any object. And what we are doing, we are folding, we are molding the strip of this line such that we will get a smooth curve. Okay. Now someone may say that if I want a sharp corner, then how do we get the sharp corner? Let's say, for example, what I want a sharp corner like this. Then, by using this BSP line, how do we get a sharp corner? For this purpose, what we can do, if we use only one sample point, let's say there is only one sample point which is at this point, then with the help of this BSP line generation method, what we get the curve which is like this, which is I am showing in the dark, what we can say dark ink. Okay, if we are having only one sample point and if we use BSP line curve generation method, then we get the curve which is of this shape. Okay, by using identical sample point, we can get the sharpness. Now, instead of one sample point, at the same point, at the same place, if I use two sample points, that means here only, if I use two sample points, then we will get somewhat sharp curve. Again, if I use three identical sample points at the same place only, then what we get? We get the sharp curve. So, like this, by using BSP line curve generation method, we can get smooth curve. If we want sharp curve, then by using identical sample point, several identical sample point, we can easily get the sharp corner curve also using this BSP line curve generation method. Then we are having Bezier curve. Next curve that we have, by using which we can draw the curve, this is called Bezier curve. Bezier is the name of scientist who discovered this method. So in respect of his name, the name of this curve is Bezier curve. Okay, this Bezier curve basically it is developed by the French engineer whose name is Bezier. Okay, so in this Bezier curve, again, in each and every curve generation method, we are using sample point. Okay, what we are doing? We are using a sample point, and with the help of these sample points, we can easily get the curve. In this Bezier curve, we can use one sample point, we can use two sample point, we can use four sample point. And with the help of this, we can get several type of Bezier curve. If we are using only one sample point between two endpoints, then we will get simple Bezier curve. If we use more than one sample point, okay, then with the help of this, we can get quadratic Bezier curve. Again, if we are using 4 sample points, then we may get cubic Bezier curve. This simple, quadratic, cubic Bezier curve. The name of these curves, it mainly depends on which type of equation we are using for generating this Bezier curve. Okay. Okay. So firstly, let's see some of the properties of the Bezier curve. And after that, we will see how this Bezier curve is drawn. Okay. So Bezier curve is the simplest curve that we can draw. Okay. First, first type of curve is what? It is the simple Bezier curve. Okay. This simple Bezier curve, by the help of the simple Bezier curve, we get a straight line from the start point to the end point. Okay. Quadratic Bezier curve, if we are having 3 sample points, if we are having 3 control points, by the help of these 3 control points, we get the quadratic Bezier curve. Okay. So quadratic Bezier curve is determined by using 3 sample points. Cubic Bezier curve, specifically to get the cubic Bezier curve, we can use 4 control points with the help of which we get cubic Bezier curve. Okay. Now let's see how we can get this Bezier curve. Okay. There are some properties of the Bezier curve. First property is that the Bezier curve must pass through the first and last control point. What about the remaining control point? We will see in detail whenever we will observe the cubic Bezier curve. Okay, here. Then the second property of the Bezier curve is the degree of the polynomial is 1 less than the number of polygon points. That means if we are using 4 control points, then to draw the curve by using 4 control points, we are using polynomial equation which is of degree 3. That's why the name of this method is cubic polynomial. Although we are using 4 control points, but we are using polynomial equation of degree 3. That's why the name of this curve is cubic Bezier curve. Okay. This Bezier curve generally follow the shape of polygon that we are using. We will see, you will understand what do you mean by this statement whenever we see in detail how this Bezier curve is drawn. Okay. Then these control points we can arrange in several ways. Okay, the direction of angle of end point is same as that of the first and last point. Okay, you will understand these things more whenever we see how this Bezier curve is generated. Okay, and the last property of this Bezier curve is the Bezier curve can be subdivided into 2 Bezier segments, which we can by joining which we can get the new shape. Let's see how this Bezier curve generated by using 4 sample points. Okay, so here if you observe, this is the first sample point, this is the second sample point, this is the third sample point, and this is the fourth sample point. Okay, now these 4 sample points either we can arrange in the first way or we can arrange this uh, 4 sample point in the second way also. This is the second way, that is particularly in Z shape we can arrange the sample point. If we arrange the sample point in this format, then we will get a shape like this, Bezier curve shape like this. If we arrange the sample point in this format, then we will get a shape like this. Okay, so by using this, what we get? We get the Bezier curve. Now, specifically, whenever this Bezier curve start moving from the starting point towards the ending point, at that time, the value of u, which we are using as a parameter in the blending function, this value of u varies from 0 to 1. Okay. At this starting point, value of u in the blending function is what? It is 0. At this end point, value of u in the blending function is what? It is 1. In between, the value of u is how much? It is 0.5. Here, if you observe, value of u is how much? How much? It is 0.25. And here, possibly, it may be 0.75. Okay. Now, I have one video that will explain through the animation. The instructor will explain how this Bezier curve, how this simple, quadratic, and cubic Bezier curve can be drawn. Okay, let me show this video through which we will understand in detail how this Bezier curve is drawn. Okay, so let me copy the URL. Okay, so this is the very good video that will explain how we can draw the Bezier curve by using animation. Okay, so I think audio is not here. So let me share this by using the audio. Okay, so I will stop the sharing and let me share the screen by using audio. मॅडम ऑडिओसाठी झूम मध्ये कुठला ऑप्शन आहे? हॅलो, कारण ऑडिओ ऐकू येणार नाही याच्यामध्ये.
हॅलो सर.
हा,
नाही, तुम्ही जर युट्यूब मधून वगैरे ती लिंक हे करत असाल, शेअर करत असाल तर येतो ऑडिओ.
येतो ना?
हो
ओके,
हो येतं.
लेट मी ट्राय दिस. फाइन, so let me share this. Let me know if audio is not here. I don't hear the audio. Do you hear it?
No sir, I am also not getting any audio.
So I think there is an option for Bezier to share these things. Zoom मध्ये ऍक्च्युली अॅनिमेशन बघू. अॅनिमेशन मधून सुद्धा समजेल थोडंफार, ऑडिओ जर येत नसेल. So here basically we are having 2 points, and if we are using the simple equation, simple form of equation, then uh, how this Bezier curve can be drawn by varying the instead of u here, he is using t. Okay, so how this Bezier curve is drawn, that is shown. Okay, so by varying the value of this u, t here, by varying the value of t, it is drawing the curve. Okay, if we are having quadratic, then in case of quadratic, how this value of t is varying, you can observe here. Okay, so with the help of this, it is drawing the curve. So that will be shown. Okay, so like this, it will draw the curve by varying the value of t. Instead of u, he is using t. Okay, so this is how the curve will be drawn in Bezier curve by varying the value of t. If you observe carefully here, by varying the value of t, it is drawing the curve. Okay, so this is the quadratic Bezier curve. Then we are having a cubic Bezier curve in which we are using 4 sample points. How these sample points will be used for drawing the cubic Bezier curve, that will be shown by using any. Okay, so see here, it is showing how this cubic equation is used for drawing the curve. So this is very nice video which will explain how these control points, how this curve is drawn by using the animation. Okay, so this is how whenever we execute the Bezier curve generation method, the curve will be drawn. Okay, so we need to provide the sample points at the place of P1, P2, P3, P4. Okay, P0, P1, P2, P3. So here P0, P1, we just need to provide the coordinate of these sample points. And with the help of these sample points, it will draw the curve. Okay, fine. So this is what I want to show you. So here, if you observe, so this is how by executing the cubic equation, we can draw a curve. Okay, probably in your assignment, you may have assignment like draw what we can say flower like this. To draw the flower like this, what we have to do, we have to provide a box like this, where this is the P1, this is the P2, this is P3, and this is P4. Okay, so by providing the coordinate in this format, what this Bezier curve will do, this Bezier curve will draw the curve in the shape like this. Okay, so like this, by specifying the appropriate coordinate, appropriate sample point, what we can do, we can draw any shape, any curved shape. कुठलाही कर्व शेप जर ड्रॉ करायचा असेल, for this purpose, what we can do, we can specify such control points, which I have shown in the green format, in a green
Sir,
color.
actually, the earlier screen is only visible, YouTube screen.
Okay, okay. Let me change this. I thought the whole screen is visible. Okay, fine. Now is it visible?
Sir. Yes, sir.
Okay. Now see here. Let me explain it again. Okay. Now, if you want to draw a flower-like structure, let's say if you want to draw such structure, to draw such structure, what we can do, we can use this Bezier curve. In Bezier curve, let's say if I want to draw such curve, for drawing such curve, what we can do, we can use the 4 sample point which is of this type. Okay, so here we are having P0, first sample point, here we are having second sample point, here we are having third sample point, and here we are having fourth sample point. Okay, so by the help of this, we get a shape of petal of a flower. Okay, so by providing such sample points, by providing the coordinate of such sample point, we can easily able to draw the curve which is of this shape. Okay, so this is how actually प्रॅक्टिकलला तुमच्या अशा टाईपच्या असाइनमेंट्स असतील. सो बाय युझिंग दिस बेझियर कर्व इक्वेशन, क्युबिक बेझियर कर्व इक्वेशन, we can draw a flower like structure. Okay, so for this purpose we need to provide, we need to use the sample point which is here. So by using these sample points, what we can do, we can draw any shape of curve. Okay, fine. So let's see what are the equations that we can use for drawing this Bezier curve. To draw this Bezier curve, cubic equations are like this. So basically here x1, this x1, x2, x3, x4, these are what? These are the x coordinate of the sample point. These are what? These are the x coordinate of sample point, or we can say control point, x coordinate of a control point. And u is what? U is nothing but it is a parameter. Okay, this u is a parameter, and whenever we execute this function, at that time what we have to do specifically, we have to vary the value of u from 0 to 1. Okay, by stepping 0.1. That means in u, what we have to do, in earlier u, we have to add 0.1. And like this, whenever this u value varies from 0 to 1, the shape will start moving from start point to end point. Let's assume that we are having sample points, and these sample points we have provided like this. Okay. And if we use these equations, okay, where this x1, x2, x3, x4, these are what? These are the coordinates. By using these equations, what we can do, we can draw such shape. Now, as we execute this for loop, where value of u varies from 0 to 1. First value of u is 0, second value of u is 0.1, third value of u is 0.2, fourth value of u is 0.3, like this. As this value of u varies from 0 to 1, curve will start drawing from the starting point to end point. And this is how, by using this Bezier curve, we can draw the curve. Okay, आपण काय करू शकतो? We can draw the curve which is of this shape. As per our control point, the shape of the curve gets varied. If you want to draw such curve, then for this purpose, what we have to do? We need to provide one control point here, one control point here, another control point here, and third control point here. Okay. So by providing these control points, what we can do, we can get the curve which is of this shape. Right? We can get the curve which is of this shape. Okay. So these are the cubic equations by using which we are getting the curve. So that's why the name of this method is cubic Bezier curve. So with the help of these cubic Bezier curve, we will get any shape of curve. So this is the Bezier curve. There is one more way by which we can draw the Bezier curve. What is that way? Let's see. Let's say what we have, we are having four control points. One control point is here, second is here, third is here, and fourth is here. Okay, so these are the control points that we have. These are the control points. What we do in the second method, we calculate the midpoint of each line segment. So for the first, let's say this is 0 point, 1 point, second point, and this is the third point. What we do, for the first line segment, we calculate midpoint. For second line segment, we calculate the midpoint. And for the third line segment, we calculate the midpoint. And we join these midpoints. Okay. Once we join these midpoints, we are again getting a line segment. For this line segment, again we calculate the midpoint. We are observing how cubic Bezier curve can be drawn by using the midpoint. Okay. Then what we get here, for these two line segments, we are getting the midpoint. Right. Again, we need to join these midpoints. Once we join these midpoints, what we get? We get one more line segment. Again, we have to calculate the midpoint of this line segment. And now what we can do, we can join these starting point and midpoint, and we can join this midpoint and the end point. And with the help of this, we can get the Bezier curve. So this is the second way by which we can easily get the Bezier curve. So these are the two ways. Either we can use cubic Bezier curve equation, with the help of which we can get the curve, or we can use midpoint. We can calculate midpoint, we can join these midpoint, and by joining midpoint and end point, we can easily get the Bezier curve. So this is the part which is related to Bezier curve, or up to this much, we are having the part which is related to curve. And from here onward, let's see second part of this unit. And the second part is nothing but it is a fractal. Okay. In day-to-day life, we are observing various natural objects. Generally, whenever we draw any curved surface, any rough surface, okay, At that time, we can use line drawing algorithm. We can use some of the equation with the help of pitch. We can draw the rough surfaces. Okay, but and we can draw the random shape of the rough surfaces. But if we observe nature, in the nature we are having mountain, we are having the ocean waves, we are having cloud, we are having trees, in which there is a kind of roughness, there is a kind of we can say randomness which we observe. And if we want to draw such natural object by using a computer system, then to draw such a natural object by using a computer system, we are having a method, we are having a way, which is called as fractal. Let's see where we can use these fractals. These fractals can be used to show the molecular structure. In chemistry, we generally observe the molecular structure of various objects. Okay, so if we want to generate this molecular structure on the digital display devices, okay, then this molecular structure we can generate on digital display devices by using the concept of fractal. Okay, or if we want to draw this natural mountain, here we are observing the randomness and roughness, right? Here, if we observe the age of this mountain, what we are observing? We are observing some repeated pattern. इथं जर तुम्ही बघितला, here if you observe carefully, there is a repeated pattern. This is one repeated pattern, this is another repeated pattern, this is another repeated pattern. Okay, in nature there are various objects which is having a repeated pattern, and there is some randomness in this repeated pattern, there is some roughness in this repeated pattern. And if we want to draw such roughness, if we want to draw such randomness by using, if you want to generate such randomness by using a computer system, by using a digital display devices, then for this purpose, what we can do, we can use fractal, concept of fractal. If you observe here a tree, this tree, this tree is having, again it is having some repeated pattern. Like here we are having a repeated pattern of leaves, a repeated pattern of a particular structure. Okay, or if you want to generate the structure of galaxy on digital display devices, okay, so to generate such complex picture by using a computer system, we can use the concept of fractal. Okay, so generally fractals are nothing but, fractals are very complex pictures which are generated by using a computer. To generate such complex picture, what we are doing, we are using only a single formula in this in the concept of fractal, and by iterating this single formula, okay, by iterating the single formula several times, we will get a natural shape of the object on the computer system. That means what we are doing, we are using only one formula, we are repeatedly using this formula by slightly changing some of the values, and by using these iteration, by slightly changing the values within one formula only, we can generate the natural objects which are specifically complex, which we cannot generate easily by using the picture generation method that we have studied till now. Okay, so let's see where, what are the areas, what are the domains, which are the domains where we can use this fractal. We can use this fractals, concept of fractals, for generating in the field of astronomy. For what purpose? To analyze the galaxy, to analyze the rings of Saturn, to generate such random and complex structure, what we can do, we can use the concept of fractal. Or in the field of biology, in the field of chemistry, if you want to depict the bacteria culture, if you want to observe the chemical reaction or human anatomy, structure of molecule, if you want to observe the structure of plants, so for generating all these things, for observing all these things on digital display devices, artificially we can generate, we can simulate these things by using the concept of fractal. Okay, basically to generate such complex structure, we are using the concept which is called as fractal dimension to get the roughness, to get the randomness, to get the complexity. Artificially we are using a concept which is called as fractal dimension. Now to explain this fractal dimension, how we can calculate a fractal dimension for any rough surface, firstly we must know what is topological dimension. Generally if we observe a line, for line what we have, we are having only a length. Line we can explain just by using a length. We don't need any other things to explain a line. Okay, that's why if we express the line by using topological dimension, then for line topological dimension is 1, and this topological dimension we can indicate by using dt, dt equal to 1. Okay, if we have a plane, then plane have width and height, that is it is having 2 dimensions. So that's why if we want to explain plane, then for plane we are having 2 dimensions. So that's why plane will have a topological dimension which is 2. Okay, whereas if we observe any 3-dimensional object, for this 3-dimensional object we are having 3 dimensions: height, width and depth. Okay, so that's why the topological dimension of 3-dimensional object is what? It is 3. Okay, so where this dt is called as topological dimension. Okay, and basically by using this topological dimension, what we do, we can specify variation of fractal object. We can specify variation of fractal object. Let's see how variation of fractal object can be observed, can be calculated by using this topological dimension. Okay, let's see how we can observe, how we can see, how we can calculate the fractal dimension. Now to calculate the fractal dimension, we will observe the relation between scaling parameter and the number of subpart that we can create by using a scaling parameter. Okay, so by observing these things, we can get the knowledge about how we can calculate the fractal dimension. Okay, so here we are using 2 factors: scaling factor and the number of subparts that are getting generated by using a particular scaling factor. Let's say, for example, we are having a line and we are scaling this line by using 0.1, 0.5, or by we can say by half scaling, by half scaling factor. Then if we scale the line, 1 unit of line, by using half scaling factor, then by using half scaling factor, how much part we are getting? We are able to generate 2 subpart by applying 1/2 scaling factor. Okay, so here if we observe here, the topological dimension of this line is how much? It is 1. Okay, soon you will get how we can correlate the scaling factor, and how we can correlate this number of subpart to depict the fractal dimension. Okay. Now let's consider that we are having a square, and if we apply a scaling factor that is 0.5, or we can say 1 by 2, if we apply this 1 by 2 scaling factor to the square, then by the help of this, we are getting 4 equal subpart of the square. Okay. So here the topological dimension of this square is how much? It is 2, right? So by the help of this scaling factor 1 by 2, how much subpart we are getting? We are getting 4 subpart. Now instead of this, if we are having 3-dimensional object, and if we apply 1 by 2 scaling factor, then with the help of this 1 by 2 scaling factor, we are getting 8 subparts. Say for example, we are having a cube, 3-dimensional cube, and if we apply the 1 by 2 scaling factor, then how many subparts we are getting? We are getting 8 subparts. Now let's try to correlate these things. Okay, we are having scaling factor, we are having number of subparts, and we are having topological dimension. We are trying to correlate these things, and with the help of this, what we are trying? We are trying to find out the fractal dimension. Okay. Now see here, scaling factor is what? It is 1 by 2. For line, if I apply 1 by 2 scaling factor, then how many subpart we are getting? We are getting 2 subpart. Okay, its topological dimension is how much? It is 1. This is for line. Now, whenever we are applying 1 by 2 scaling factor for square, 2-dimensional square, okay, 2-dimensional square, then in such cases, we are getting 4 subparts, where topological dimension of the square is how much? It is 2, right? And if we talk about the cube, then by applying this 1 by 2 scaling factor, we are getting 8 subparts, where the topological dimension of this cube is how much? It is 3. Okay. Now see here, if I want to get the original object, then for line, what I have to do? I have to multiply the scaling factor with the number of subparts, right? For square also, what we can do? We can, if we multiply these things, okay, then we are getting the original. That is, to construct the original square, what we have to do? We have to combine these 4 subparts. Okay. So by the help of this relation, by using the above observation, we can find out the relation between the number of subpart and scaling factor. And that relation is nothing but it is n into s raised to df, or we can say dt. That is, if we apply this formula here for line, then what we have? What is the amount of n? It is 2. What is the amount of s? It is 1 by 2. What is the amount of dt or df? It is 1, right? If we perform this operation, then what we get? We are getting the original output. For square, what we have? We are having 4 subparts that we are getting. Value of n is how much? It is 4. Okay. How many? What is the scaling factor that we are applying here? We are applying 1 by 2. What is the topological dimension that we have here? Here we are having 2. That means what we can say, 4 into 1 by 4 we are getting. We are getting the original value, right? Same thing applicable for cube also. For cube, we are having 8 subpart. Value of n is 8, right? Scaling factor is 1 by 2, and the topological dimension of cube is how much? It is 3. Okay. If you perform this operation, then what we are getting? We are getting 1 value of 1. So this is the relation which explain how we can find out the topological dimension, or we can say this fractal dimension. Okay, if you modify these, if you simplify this formula, then we will get this formula. Okay, so by using this formula, what we get? We get the fractal dimension. Okay, so this is how, by correlating the number of subpart and the scaling factor, we can find out the fractal dimension. Okay, so this is how we can find out the variation in the object by observing the number of subpart and by observing the scaling factor. Okay, now let's see some of the types of fractal. Fractal classification, types of fractal. Okay, before that, I am showing you one picture. This is a हे कशाचं पिक्चर आहे? चाफा, चाफ्याचं झाड, चाफा आहे. ओके, नाव हा चाफा मी का दाखवतोय ते तुम्हाला समजेल थोड्या वेळात. ओके, नाव सी हियर, बेसिकली there are three types of fractals we are having. What are these three types of fractal? Self-similar fractal, self-affine fractal, and invariant fractal sets. These are the three types of fractals that we have. Self-similar fractal, it is a type of fractal in which, if we observe the structure of entire object, then in the entire object we are observing the number of subparts, and these number of subparts are what? These are nothing but these are the scaled down version of the entire object. Okay, so such type of fractals can be constructed by applying a scaling factor to overall shape. Okay, this scaling factor can be similar or it can be different, and with the help of which, what we can do, we can get a self-similar fractal. Okay, statistically, what we are doing here in the self-similar fractal, by using random variation, we can generate model of trees, model of shrub, or any other plant. If we want to generate such type of structure by using digital display devices, then these we can do by using self-similar fractal. Okay, आता हे जर तुम्ही हा आधीचं जे मी पिक्चर दाखवलं होतं, याच्यामध्ये जर तुम्ही ऑब्झर्व केलं, चाफ्याचं जर झाड बघितलं, तर याला काय आहे? एक ब्रँच आहे, आणि या एक ब्रँच पासून दोन ब्रँचेस तयार झालेले आहेत. ओके, आणि चाफ्याचा दुसरा कुठलाही सबपार्ट बघितला तर असाच आहे, फक्त हा स्केल्ड डाऊन व्हर्जन मध्ये असतो. बघा, इफ यू ऑब्झर्व हियर, ओके, there is one branch, and for this one branch we are having other two branches, okay, which is similar to this one. Only the thing is that here the scale is larger, the size of object is larger, and here the scale is what? It is smaller. Okay, if you observe here we are having one subpart, and from this one subpart we are getting two subparts, right? किंवा इथं जरी तुम्ही ऑब्झर्व केलं, here also if you observe, here we are having one subpart, and from this one subpart we are getting two subparts. So this is the best example of self-similar fractal, right? So if we want to generate such structure by using a computer system, then for this purpose we can use self-similar fractal. Okay, then the next type of fractal is self-affine fractal. In the self-affine fractal, basically there is a small difference between self-similar fractal and self-affine fractal. In the self-similar fractal, what we have, we are applying scaling to x, y, and z coordinate equally. But in self-affine fractal, we are applying scaling parameter to each coordinate differently. म्हणजे x ला वेगळा स्केलिंग फॅक्टर अप्लाय करतोय, वी आर अप्लाइंग scaling factor, different scaling factor for x coordinate, different scaling factor for y coordinate, different scaling factor for z coordinate. So by applying different scaling factor, we can easily get this self-affine fractal. Statistically talking, in this self-affine fractal, again, what we are doing? We are applying a random variation. Where do we use this self-affine fractals? We use this self-affine fractal to model the structure of terrain, to model the structure of water, to model the structure of cloud. Okay. The third type of fractal is nothing but it is invariant fractal set. Invariant fractal set, this invariant fractal set, it is formed with the non-linear transformation. By applying non-linear transformation to the fractal, what we get? We get invariant fractal set. Basically, here, which this invariant fractal set include self-squaring fractal, just like Mandelbrot set. Mandelbrot set, to generate Mandelbrot set, we use the invariant fractal set type of fractal. Okay. Now let's see some of the fractals which we can generate by using the repetition and by providing some randomness. Okay. First type of fractals which are there is called as Hilbert curve. Although the name of heading for this concept is Hilbert curve, but it is under the fractal. This is the part of fractal. Okay. So this Hilbert curve is also called as a piano curve. Why it is called piano curve? Piano curve you will get soon, because the structure of this curve looks like a piano. So that's why the name of this curve is what? It is a piano curve. Okay. Generally, this Hilbert curve start from a square. Okay. Initially, to generate this Hilbert curve, we are having a square. This square we subdivide into 4 equal parts. After subdividing this square into 4 equal parts, we calculate the center point of each subsquare. And in this Hilbert curve, we join these center points. Okay. So this is the output after first iteration. After first iteration, we will get this output. Okay. Now, in the next iteration, what we do? We again divide each subsquare into 4 subsquare. Okay, that means this subsquare, it is again divided into 4 subsquare. This subsquare is again divided into 4 subsquare. This subsquare is again divided into 4 subsquare. This subsquare is again divided into 4 subsquare. Once we get the subsquare, again we calculate the center point of each subsquare. What we do? We again calculate the center point of each subsquare and we join these center points. But this time, instead of straightforward joining, what we do? We apply some variation. That is, let's say we may join these points like this. Okay, we may join these points like this, and we can go on like this. Okay. So so like this, what we can do? We can connect these things. So which looks like a piano. Okay. After applying second iteration, we may get the output like this. Okay. What we get? We may get the output like this. So it looks like a piano. So that's why the name, alternative name for this Hilbert curve is what? It is piano curve. Okay. So using the repetitive operation, using the several iteration, we can fill the space. So again, this Hilbert curve is nothing but it is used to fill the space. This is called space filling curve also. Okay. Ideally, if you observe, the length of this Hilbert curve is infinite. But in each iteration, the length of the curve, it is increased by a factor of 4. Initially, let's say if the length of curve is 4, then after first iteration, it will be increased by 4, factor of 4. Okay. So this is what the Hilbert curve. This is how by repeating the iteration several times, what we are getting? We are getting the complex structure. So that's why this Hilbert curve comes under the concept of fractal. म्हणून हा हिल्बर्ट कर्व कशाच्या अंडर आहे? फ्रॅक्टलच्या अंडर आहे. Why? Because the picture that is getting generated, it is a what we can say complex picture which is having some randomness in the nature and which is somewhat rough. So that's why this is called a fractal. Okay. Conceptually talking, the topological dimension of this Hilbert curve is 1 and fractal dimension is 2. Variation in the curve is how much? That is denoted by using fractal dimension, and the fractal dimension of this Hilbert curve is how much? It is 2. Okay. So this is the Hilbert curve. The next type of curve or the next type of fractal that we have, okay, so such type of output we get if we iterate, if we perform number of iterations on the Hilbert curve. Okay, initially we are having a empty square. Okay, by dividing this empty square into 4 subpart, again into 4 subpart, again into 4 subpart, and by connecting the center points randomly, what we get? We get the shape, we get the output like this. Okay, so this is nothing but this is the we can say piano curve, right? So this is the Hilbert curve, piano curve, and this comes under the fractal. This is the part of fractal. Okay, the next type of fractal or next type of curve that we have, the next fractal that we are going to observe, the next type of technique that we are going to observe for generating fractal, it is called as Tradiac-Koch curve. Generally, this Tradiac-Koch curve is used to generate the structure of snowflakes. Initially, in this Tradiac-Koch curve, or in simple word, it is called as Koch curve, Koch fractal. Initially, in this fractal generation method, we are having a straight line. This straight line, it is divided into 3 equal parts. Okay, and whatever middle part we have, this middle part, it is replaced by 2 sides of equilateral triangle. This middle part is simply discarded and this middle part is replaced by 2 sides of equilateral triangle. And this is how we get the output after the 0th iteration, after the first iteration. After first iteration, we get the output like this. And again, we perform this process repeatedly. That means for this line segment, again we repeat this process. This line segment, again it is divided into 3 subparts. This line segment, again it is divided into 3 subparts. This line segment, again it is divided into 3 subparts. This line segment, again it is divided into 3 subparts. And whatever middle part we have, this middle part is discarded, and this middle part is replaced by the equilateral sides of a triangle. Okay, and this is how, by using this Tradiac-Koch curve, we get the fractal. Okay, let me show this by using a triangle. Let's say we are having such triangle, and if we apply the procedure of Koch curve for this triangle, Then after first iteration, we get this output. If we again apply the Koch fractal method, then we will, in second iteration, we will get this output. In the third iteration, we will get this output. So like this, complexity and randomness to the object we are getting by using repetitively applying the method, repeatedly applying some randomness. Okay, so this is the Koch fractals by using which we can generate the complex structure. Okay, again I am showing this picture because this is the real life example where we can say that such type of structure we can generate by using the fractals. Okay, how we can generate this, let's see. So this picture shows we are having one branch initially. From this one branch we can generate three branches. From these three branches we can again generate three branches for each sub branch. And like this, by performing iteration repeatedly for several times, we can generate the complex structure. Okay, so this is how we can generate fractal tree. If you want to generate fractal phone, then this also we can generate like this. Initially we are having one line segment, then this one line segment again if we repeat the process, then we may get several line segments by applying different scaling factor. Okay, so after different iteration, after several iteration, we may get a structure like this. Okay, so which is generally used for generating the animation. If we see any animation, if we see any cartoon, then artificially complex objects are generated by using the concept of fractals. Okay, snowflakes are generated like so. Again, this is the best. This is one more example which shows a very complex structure which we can generate by using the fractal. Okay, so these are some of the concepts that we have in the unit of fractals, curves, and fractals. Okay, so whenever I used to teach the any concept at that time, I prefer to show them or I prefer to discuss with them the applications of these concepts, applications of the concepts that we are learning. So basically, if we observe curve and fractal, these curves and fractals we can use to model the structure of terrain, to model the structure of cloud, water, trees, plants, feathers, or various surface structure. Also, if we want to model the distribution of stars, distribution of river, Iceland, moon creature, okay, so such type of structure we can generate by using the fractals and curves. Or if you want to show variation in the stock market, share market, so the variation in the share market we can show by using the curves and fractals. If you want to show the traffic flow, if you want to show the music symbolically, if you want to show the utilization of urban properties or boundaries of converging regions in the numerical analysis technique, then these are some of the fields where we can use the concept of fractals, where we use the concept of curve, with the help of which we can generate artificial object which looks like a real world object, which looks like a natural object, which is having very complex structure, which is having some type of roughness, which is having some type of randomness. Okay, so this is the concept I think which is there for your syllabus, and this much knowledge is enough for you, which will provide us the detailed understanding related to curves and fractals. Okay, thank you. If you have any questions, I always welcome. Okay, from my side, it is over. So if anyone want to ask anything, you may well.
Okay. Yes, students. Any questions from your side? Yes.
क्वेश्चन येत नसतील तरी याचा अर्थ एक आहे, एक तर मी सांगितलेलं सगळं समजलंय किंवा काहीच समजलं नाही.
Can at least, yes, students, you can at least tell whatever your feedback is there about the lecture.
आय थिंक मी असं समजतो की मी सांगितलेलं बऱ्यापैकी समजलंय मुलांना, म्हणून क्वेश्चन नाही.
Yes, sir. Understood.
Okay. So the concept is simple. The concept is very short. Only you need to understand these concepts where in real life these concepts are used.
Yeah, okay, if you have any doubts, you can type in chat box also.
Yes, if you hesitate to talk in front of all the students, you may put in a
You
chat
can
also.
give feedback as well as you can put the question in the chat box. We can see that.
Or later on also, if you want to ask anything, I will provide my email ID with madam. So she will share my email ID. You can ask me a question later on. Okay. So I taught this subject for 9 years. 9 times I have taught this subject. So I have this knowledge about the things that we have studied in computer graphics. Okay.
Yes, actually, I must say that the lecture was very nice, right from the basic concepts like how to draw the line and how to draw the curves, etc. Sir has explained very well. He has covered all the curves, B-spline curve, Bezier curve, and its properties and their generation, the methods of curve generation, and again the fractal part, the types of curves like Hilbert curve and Koch curve, and how we are generating the fractals. So sir has explained it very well. So if you don't have any question, I suppose that the points are clear to you. No any doubt, right? Girls? All of you have understood?
Yes, ma'am.
What about boys?
Yes, ma'am. Yes, ma'am.
Okay. Thank you. Thank you for your feedback. So on behalf of Sveris College of Engineering, Pandharpur and CSE department, I thank Professor Panchal sir for his valuable guidance in this area, and took out the time out of his schedule and guided the students in computer graphics. So thank you, sir. The session was very nice. Thank you so
Thank you.
much.
I would also like to thank you for inviting me for this guest lecture. I'm always eager to provide such knowledge, to spread such knowledge among the students.
Yes, sir.
Thank you.
Thank you so much. Thank you. So I declare here the session is over. So student, all of you can leave the session now, and the further guidelines will be given for you if any next sessions are there. Thank you, sir. And thank you all
Thank you.
students.
Thank you.